Oh, we are live. Okay. All right, let's bring up the thingamabob and boop. So, naming ionic compounds. So, naming ionic compounds isn't the most difficult thing in the world, but it is going to take a lot of memorization and a lot of practice. Okay. So, the name of an ionic compound is always going to be the name of the cation followed by the name of the anion. Remember, cation means positive ion, so we're going to mostly be talking about metals, but there are polyatomic cations. Anion means negative, so mostly nonmetals, but there are a lot of polyatomic anions. A polyatomic ion is a molecule with an ionic charge. That is to say, a covalent compound with a charge. So, there are three kinds of cations and two kinds of anions. So your cations can be univalent, multivalent, or polyatomic. Univalent means they only take the one charge. So those are the ones that I called the easy ions last time. Meaning the alkali metals, the alkali earth metals, and the staircase, silver, zinc, and aluminum. Those guys can only take one kind of charge. They only form one kind of ion. That said, am I even making a sound? Yes, I am. Good. Okay, that said, the alkaline metals take 1 plus, the alkaline earth metals take 2 plus, and then silver, zinc, aluminum, it's 1 plus, 2 plus, 3 plus. So those are the univalent. They only form one kind of ion. The multivalent can make more than one kind of ion, so they're going to be a little bit more complicated. Because with the univalent ions, you just have to name the metal, and you know what charge that ion has. But with the multivalent metals, it's you can't know what the charge is just by naming the metal. So you also have to indicate what the charge is. So that's the difference between those two. With the univalent monatomic cations, that is to say, with the first two columns or the staircase, you just name the element, and that's the name of the cation. But for the multivalent ones, you have to name the element and then you use a Roman numeral in parentheses in order to name the cation. So, for example, the name of sodium 1 plus is just sodium. Okay, the name of magnesium 2 plus is just magnesium. Oh, poo on a stick. The stupid camera's not... Okay. I'll be back in about 5 seconds once I get the camera working. Alright, hopefully... Okay, hopefully we got this without too much of a hitch. It looks like it's still going. Okay. Excellent. I was able to pop back in and out easy enough. Okay, so sodium, because it's monovalent, the name of the ion is just sodium. Magnesium, it's, univalent, not monovalent. Magnesium only forms the one kind of ion, so it's just magnesium. But iron can form multiple ions. You can have iron 2 plus, or you can have iron 3 plus. So the name of the ion has to include the charge of the ion. So iron 2 plus is iron 2, iron 3 plus is iron 3. Personally, I use lowercase letters for the Roman numerals because when you use uppercase letters, it is really easy to confuse things like 3 and 4 if you're writing fast. So I use the lowercase letters just because it's a little bit harder to screw up, especially if you have bad handwriting. All right, what are you doing over there, cat? All right, you're not breaking anything yet. Okay, now, there are also polyatomic ions. Polyatomic ions, like I said, those are covalent compounds that have a charge. There are some trends when it comes to the names of polyatomic ions for some of the ions, but for the most part, you're just going to have to memorize them. Now, for the cations, you're kind of fortunate in that there are very few polyatomic cations. So off the top of my head, the only ones I can remember are ammonium, Hg2, that's mercury 1, and can I think of any others? Those might be the only two. There's got to be more, but I can't think of them. All right. Like I said, there are very, very few polyatomic cations. All right, so just be aware, ammonia there's the cat, as always. NH3 is ammonia, NH4 plus is ammonium. Again, depending on the way you talk, that might or might not be more or less clear. This is just the way that we do things, and since we've been doing it this way for centuries, we absolutely are not going to change it. Now, for this guy, we have mercury 1. Because there are 2 mercury atoms bound together with a total of a 2+ charge. And thus, it is sort of like each one has a 1+ charge. That's not how it is. The entire thing has a 2+ charge, rather than each mercury atom having a 1+ charge. But still, we call it mercury 1. And we distinguish that from the regular mercury ion, which is just Hg2+, which is mercury 2. So mercury 1 is the only, again, polyatomic ion I can think of that looks like it would be a regular monatomic ion. All right, now for the anions, things are a little bit simpler and a little bit more complicated, because you just have the monatomic ions. The nonmetals just form a single atom with a charge, and then you have the polyatomic anions. So you don't have to worry about different kinds of monatomic ions like you do with the metals. But you do have to worry about how you name those monatomic ions. Because, again, thanks to history, we changed the name. You have heard of sodium chloride, perhaps, for table salt. Well, that's because we changed the ending of the element always to IDE. So, for example, Cl1-, chlorine becomes chloride. O2-, oxygen becomes oxide. N3-, nitrogen becomes nitride. C4-, carbon becomes carbide. So we just take the end of the element and replace it with IDE. It can be a little bit arbitrary sometimes, like for most of them we drop the final INE and replace it with IDE, and that works just fine. Fluorine, fluoride, chlorine, chloride, iodine, iodide, right? But then oxygen becomes oxide, nitrogen becomes nitroide, right? So it's kind of weird. But again, it's just a matter of memorization, and there's only 10 of these guys. In fact, I could probably list all of the nonmetals really straightforwardly and easily. F-, I-, Br-, who am I missing? S2-, Se2-, P3-. I think that might be all of them. So fluorine becomes fluoride. Note that it's UO, not OU. I'll make fun of you. Iodine becomes iodide. Bromine becomes bromide. Sulfur becomes sulfide. Don't try to talk and write at the same time. Selenium becomes selenide. Phosphorus becomes phosphide. We extend this sort of naming convention to other things even when we're not talking about nonmetals, like tellurium would become telluride, things like that, which is an issue when you're looking at alloys and semiconductors, but not so much here. All right, so those are just the nonmetals. You replace the ending of the ion, you take the element name, replace it with IDE. Now the polyatomic anions are a real pain in the keister because there's like 5,000 of them. There are so very, very many polyatomic anions. And there it's just a matter of getting used to them and remembering them. And until then, you'll always have access to a chart of the polyatomic ions. So even on the test, you'll have a chart of the polyatomic ions. I mean, you can't have a chart of all the polyatomic ions because that's not possible. There's like a nearly infinite number of them. But you'll have a chart of the most common ones. So, for example, here are some of the... hydronium. I knew there was a third one. So ammonium is is the most common polyatomic cation. Hence, it's the only one in this chart. But you might occasionally run into mercury 1. Hydronium is technically the ion for acids. We almost always use just H+, but technically it's actually H3O+. And then over on the right you have a very small selection of the polyatomic anions. You'll notice that most of them end in ITE or ATE. So here we have chlorite, and here we have chlorate next to it. We have a phosphate, carbonate, permanganate, right? Most of the polyatomic anions end in things like that. Here's acetate. But there are a few exceptions that you'll need to learn how to recognize. They instead of ending in ITE or ATE, they end in IDE, ide. So the first one is right here, CN1-, that is cyanide. Then let's see, we have OH1-, that is hydroxide. And then over here on the right-hand side, O2-2- is peroxide. Those, again, are the only three I can think of. Those are polyatomic ions that end in IDE. Most of the time, if it ends in IDE, you're looking at an element. But for those three, those are polyatomic ions that end in IDE. Most of the polyatomic ions in ite or ate. But learn to recognize cyanide, hydroxide, and peroxide. Now, acetate is one of the more popular anions. When I say popular, I mean that it shows up in real labs all the time because it's cheap. It's vinegar. So acetate is everywhere. So CH3CO2 is one way of writing it. Another way of writing acetate is C2H3O2 1-. Another way is CH3COO 1-. Or this is especially popular in organic chemistry. Organic chemists love this sort of abbreviation, AC 1- for acetate. The reason there are so many different ways of writing it is because people are idiosyncratic. People like doing random shit. This one here, for example, emphasizes what I discussed in the lab lecture, if you looked at that, when it comes to this sort of carboxylic acid and resonance and things like that. This one just shows the atoms, this one shows a bit of connectivity, and this one is just a lot quicker to write. And that's why the organic chemists do it that way. So, like I said, there's not much for it but to get used to the way we write these things, the way we name these things, and just learn to recognize these ions, connect name to formula, formula to name. Until you get really good at that, it'll be a matter of looking them up. Before we go on, let's see, I believe... No, I didn't. Okay. So, there's a couple of things. Naming conventions. If you look right here, you'll see HCO3 1-. That is hydrogen carbonate. Over here you see CO3 2-. That's carbonate. If you have multiple negative charges on an anion, then you can get a sort of partially balanced anion. So in this case, the carbonate, the CO3 2-, has sort of attached itself to an H plus ion, partially but not completely neutralizing the charge, leaving you with HCO3 1 minus. So in addition to sometimes calling that hydrogen carbonate, the far more common is bicarbonate. So again, if you're a baker, sodium bicarbonate is when you take this and you combine it with a sodium ion. Similarly, you have here hydrogen sulfate or bisulfate, which is the SO4 2 minus or sulfate anion combined with an H plus to make HSO4 1 minus, and thus hydrogen sulfate, or less commonly bisulfate. That is an older convention where you can take one of these guys, combine it with an H plus ion to make a bi version of the thing. So you could have a bisulfite or a bichromate or something like that. It's getting fairly rare. I've only seen it once where you'd have a bisulfate. Actually, it might have been a bisulfite. I don't know, but it's possible. And I think the guy who made that particular jug was European, so maybe that's why. This hydrogen sulfate is a slightly more common sort of thing. So you might see, instead of sodium bisulfate, you could see sodium hydrogen sulfate to indicate that the SO42 minus has been bound with a hydrogen H plus and a sodium Na plus. Similarly, up here you have a dihydrogen phosphate. Phosphate has a 3 minus charge. You see it down here in the lower right. If you combined it with a single hydrogen ion, you could partially neutralize it and you'd end up with HPO4 2 minus to make hydrogen phosphate. And then you add another H plus ion to continue, but not completely neutralizing it, and you'd have dihydrogen phosphate. Okay. All right. Now, if you look at this list of ions right here, okay, almost, the first ones you see, if you read from left to right, you have ClO 1 minus, ClO2 1 minus, ClO3 1 minus, and ClO4 1 minus. Hypochlorite, chlorite, chlorate, and perchlorate. It is very common with these ions to see this sort of thing. Oxygen loves to produce polyatomic anions. You'll see that most of these, the overwhelming majority of these guys, have oxygen in them. Those are called oxyanions or oxoanions. Okay? And lots and lots of different compounds form them. So here we see chlorine combined with oxygen. Here we have phosphorus combined with oxygen. Here we have sulfur combined with oxygen. Chromium combined with oxygen. Carbon. Here's nitrogen. Here's manganese. So very common. Here we're going to talk about a trend, or a set of trends, a collection of trends that affect how these things are formed and how they're named. These are the most common of the polyatomic anions that you're going to be dealing with. Again, mostly because they're cheap. These guys show up all over the place in nature, particularly these guys here on the left. But these over here on the right are also popular in chemistry class. So, over here on the left, carbon, nitrogen, phosphorus, and sulfur. They will combine with oxygen to produce a pair of ions, 2 different ions, okay, with differing numbers of oxygens. So carbon can combine with 2 oxygens or with 3. Nitrogen can combine with 2 or with 3. Phosphorus and sulfur, it's either 3 or 4. 3 or 4. They all have different charges. So for carbon, their compound, the oxyanions with carbon have a 2 minus charge. Nitrogen is a 1 minus charge. For phosphorus, it's 3 minus. For sulfur, it's 2 minus. So there's the first trend. When you take on a particular row, you take a step to the right, the charge goes down by 1. So carbon is 2 minus, nitrogen is 1 minus. Phosphorus is 3 minus, sulfur is 2 minus. And then, between the rows, you go down a row, the charge goes up by 1. So from 2 to 3, from 1 to 2. Okay? So that might help you to remember these things, maybe. In the end, there's only 8 ions here, so maybe it'll just be a matter of memorizing them. Now, This is where the ITE and ATE comes into it. Okay. Let's bring back up this guy, Fuzzy McGee. All right. So we have 2 ions in each of those, for each of those elements. So let's look at carbon. Oops, 2 minus, and CO3, 2 minus. Come on, there we, all right. So O2 and O3. Each of them has a name based on carbon. And as you saw on the previous page, it's going to either be ITE or ATE, ITE or ATE. So, really straightforward. ITE, ATE. Okay. Fewer carbons, it gets the I. More carbons, it gets the A. Why? Because this guy is light on oxygen. This guy 8 more oxygen. Okay, that's not the actual explanation. I don't know what the actual explanation is. It's probably an accident of history. Nevertheless, you'll probably remember this. It's stupid, but you'll never forget it, and that's all that really matters. Light on oxygen, 8 more oxygen. Okay, so next up. So this same pattern holds for all of these guys over here on the left. NO2 1 minus is nitrite. NO3 1 minus is nitrate. Phosphite, phosphate. Sulfite, sulfate. Now, it's a different number of oxygens. 2 and 3, 2 and 3, 3 and 4, 3 and 4. Nevertheless, the ion that has 1 less oxygen is ite. The ion that has 1 more oxygen is ate. Okay. Now, coming over here to the right, we see a similar sort of pattern. Sort of. You have chlorine, bromine, and iodine. Okay, the 3 halogens. Fluorine doesn't do this. Fluorine is extreme. It doesn't do this same sort of thing. Now, over here for these halogens, not only do they form oxyanions, but they form 4 oxyanions. Now, to make it simpler, they're always going to be 1 minus. To make it more complicated, there's 4 of them. Okay, so just ITE and ATE isn't going to cut it. Okay, so we need to expand on that list. So that's why we have hypo and per. Okay, so let's go ahead and look at this. We have ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. The 2 in the middle get the regular naming convention. So the one that has 1 fewer is chlorite. The one that has 1 more is chlorate. So what the naming convention does is that it expands on that. So it has 1 fewer and then 1 more beyond just those 2. And we do that with hypo and hyper, not Kuiper, but hyper. So the Greek, in the Greek, hypo means less or weak. Hyper means stronger or more. So for hypo, you have the hypodermic needle. It injects things under your skin. You have hypothermia, when your body temperature gets too low. Okay. For hyper, you have hyperthermia, when your body temperature gets too high. That's a fever. Or hyperactive, when your little brother just won't calm down, right? So that's how we indicate even fewer oxygens is going to be hypochlorite. Okay. And then when we have even more oxygens, it's not hyper, it's just per. So perchlorate. Okay. So the 3 halogens, chlorine, bromine, and iodine, they all do this. Okay, so you could have hypobromite, you could have periodate, right? So that is a very limited selection of the polyatomic anions. These are the most common, these are the most popular, but there are lots and lots more beyond this. Knowing ite versus ate can give you kind of a hint, but not always, because let's go to the previous screen. You'll see chromate and then dichromate. Like, what the hell? Dichromate, you've kind of put two chromate molecules together. It's weird, but you know, so it's not always going to work. Then you have thiosulfate, where you take a sulfate and then you put another sulfur atom on there. What are you going to do? It's a matter of custom and getting good at reading a table of polyatomic ions. That's really all there is to it. Until you have these memorized, then you're just going to have to consult the table. I wouldn't recommend sitting down and deliberately memorizing these things. It'll be just like language. You know, you pick it up as you go along. Okay, because you'll always have a table available in this class. Okay, so you have to be able to go from name to formula, formula to name. You have to be able to go from iron 3 hydroxide to FeOH3, or calcium nitride to Ca3N2. And you have to be able to go in the other direction. CaCO3 is calcium carbonate. Na2O2 is sodium peroxide. So, I'm going to go through and do some practice. So we have ammonium chloride, or well, NH4Cl, FeNO3, and so on. Okay. Definitely, absolutely, I want you to go ahead and practice the hell out of these things. Otherwise, there's no way you're going to be able, not practice generally, don't necessarily practice these same 10 over and over again, but get good at these. You absolutely have to. It's the only way you're going to get good enough to do well in the class, to do well in the test, if nothing else. So first up, NH4Cl. Okay, we see more than two atoms, so we're dealing with at least one polyatomic ion. So, NH4, okay, and Cl. Even if you don't have the polyatomic table handy, this is just like I said, the most popular polyatomic cation. Okay, that is NH4 plus. Okay. Now, when it comes to ionic compounds, like I said in a previous lecture, these formulas always represent a ratio. Okay, so the way we set up that ratio is we have to neutralize the charge. Okay, the positives and the negatives have to balance out. Okay, so in this case, you have one ammonium ion, you have one chlorine ion or chloride. The only way they can balance is 1 minus and 1 plus. Okay, so again, once you've identified the ions, it's just a matter of naming them. You have ammonium and you have chloride. Okay, so NH4Cl is ammonium chloride. Next up, FeNO3. Note the use of parentheses here. Okay. NO3, polyatomic ion, and then there are 3 of them. So the parentheses are there to indicate that you have multiple of this polyatomic ion. Notice that up here we have a polyatomic ion without parentheses. If there's only one of it, you don't need to indicate that you have one of the thing. Hence, we don't have a 1 under the Cl. We also don't have a 1 under the ammonium. But we have more than one nitrate. That's what this is, nitrate. So we have to use parentheses, and then we put another 3. Because if you didn't have parentheses and you just wrote NO33, then that would look like 1 nitrogen and 33 oxygens, and again, I would make fun of you. Okay, so FeNO3, 3. Okay. So polyatomic ion, once you get good at naming it, you'll know right off the bat that this is, let's go ahead and just say NO3 1 minus, okay, aka nitrate. Okay. But I am making it a point to write it out as NO3 1- because, again, like I said, we have to balance the charge. And that matters because this is a multivalent metal. We don't necessarily know what the charge is just by looking at it. Therefore, the name of the ion has to include the charge in Roman numerals. So we have to find out what the charge is on this iron. So we know it's, Fe something. It's going to be iron something nitrate. Okay? So we need to find out what the charge is on this iron. Whatever the charge in the iron is, it has to balance out the charge from the nitrate. Okay? So the whole thing overall is neutral. There are 3 nitrates. Each of them has a -1 charge. So another way to put this is iron plus the 3 times the nitrate is equal to 0. They have to balance out to a neutral charge. So iron plus 3 times the charge of nitrate equals 0. The nitrate has a -1 charge, and there's 3 of them. So iron minus 3 equals 0. Iron equals +3. So the iron has a 3+ charge. That's how it balances out the nitrate. Or to put it another way, there have to be 3 nitrates for every 1 iron, because each nitrate has a -1. The iron has a total of +3. Okay? So iron has a +3 charge, and the name of this compound is iron 3 nitrate. If you don't include that 3 in Roman numerals, you haven't actually named this ion, and you'd get it wrong. Next up, TiBr4. All right. So Br, that is an element all by itself. So as an anion, that's pretty simple. We recognize that this is bromine. So the ion we're talking about is bromide. Br 1-. Bromide. What about this guy? Okay, Ti over on the left. Okay. Well, until you get good at recognizing the elements and where they come from, you have to look on the periodic table. Ti is not this guy down here. That's thallium. That's Tl. Ti is up here. Element 22, titanium. It is not here on the far left. It's not in the S block, nor is it on the staircase. So titanium can form more than one kind of ion. So its name is going to have to include the charge. We're going to have to put on that Roman numeral. So it is titanium something. Titanium with some kind of charge. Well, there are 4 bromines, and they have to cancel out that 1 titanium. So titanium minus 4. Each bromine has a -1 charge. There are 4 of them. So titanium minus 4 equals 0. Titanium equals +4. You don't have to write it out every single time, but if you're not particularly good at juggling numbers in your head, you might want to. So that means that titanium 4+. So this is titanium 4 bromide. All right, moving on to the next page. To save myself a little bit of time, I'm going to go ahead and shift this over to the other side of the screen. Haha, now we can see both of them. Okay, so it's going to take a minute to focus. Next up, we have Cu3P. Sounds like an elementary school joke. Okay, so Cu is copper. Copper is in the middle of the periodic table again. Wow, that just refuses to focus. All right, copper is in the middle of the periodic table. It's right here. It is not in the S block, nor is it on the staircase. It's right next to the staircase, but it's not on the staircase. So it can form multiple ions. So we're going to have to include the charge. So this is just an anion, a monatomic anion. In fact, it is phosphorus, P3 minus. We know this because, once again, phosphorus is right here. It is 3 steps away from argon. 1, 2, 3. 1 step to sulfur, 1 step to chlorine, 1 step to argon, meaning it's going to take a -3 charge. All right, so phosphorus takes a -3 charge. There are 3 of the copper ions. They have to balance it out, so each of them will have a +1 charge. So that means that this compound is named copper 1 phosphide. Next up, we have SnSe2. Again, nothing but monatomic ions. So the real trick here is to identify where in the periodic table this metal is and what the charge is on the nonmetal. So Se is right here, right next to bromium. Sorry, bromium. It's right next to bromine. So it's going to be 1, 2. It's going to take a -2 charge. Sn, the metal, that's tin, is right here. It is not on the staircase. It's not on the S block. Therefore, it is going to take multiple charges. We're going to have to indicate what the charge is in the name. So SnSe2. So 10 something selenide. The selenium takes a -2 charge. There are 2 of them. There's only 1 10. It has to balance out that charge. 2 of the -2s makes a total of -4. We need a total of +4 to balance it out. There's only the 1 10, so it has that entire +4 charge. So SnSe2 is 10,4 selenide. PbSO4, 2. So we have a polyatomic ion, so you have to go back and look at the chart. SO4 is over here. That is sulfate with a -2 charge. So sulfate has a -2 charge. And there's 2 of them. So whatever this metal is, the Pb, it's going to have to balance that out. Okay. Do we need to indicate what that charge is? Well, we look it up on the periodic table. Pb is right here below 10. Not on the S block, not on the staircase. We're going to have to say what the charge is. So there are 1 of it to balance out the 2 sulfates. Each sulfate is -2. So 2 -2s gives you a total of -4. So the lead has to have a +4 to balance it out. So that means that we are looking at lead 4 sulfate. BeHCO3, 2. Back to the periodic table. Be is over here on the left. It's in the S block. We are not going to have to indicate what the charge is. All we have to do is name it, okay? Because it will always have the same charge no matter what. It is just beryllium with a 2+ charge. Since it always has a 2+ charge, we don't have to indicate that. It's just beryllium. Now for the other thing, we have to, well, memorize our whatchamacallits, memorize our polyatomic ions. Until then, we look it up on a table of polyatomic ions, and HCO3 right here. That is hydrogen carbonate or bicarbonate. So there are 2 different ways you could name this compound. You could name it beryllium hydrogen carbonate or beryllium bicarbonate. Personally, I would accept either one. But on the test, they might not. I don't know. So don't base your answers on me necessarily, but on what the textbook suggests. If the textbook gives you a problem with bicarbonate in it, and it tells you to use hydrogen carbonate, go with hydrogen carbonate. If it tells you to go with bicarbonate, go with bicarbonate. Okay, next up, Mn2SO3 3. Hopping back over to the periodic table. And putting that away. All right, Mn. Right here in the middle. Manganese. It can take multiple ions. Not S block, not staircase. Shoot. Mn is manganese. Remember, don't get manganese and magnesium confused. And then we have a polyatomic ion. Again, just a matter of memorization. This one is sulfite. Second row starts at 2, third row starts at 3. Oh, that's a mnemonic I forgot to give you last time. Okay, so when it comes to both charges and numbers of oxygens, the second row starts at 2, meaning that carbonite has 2 oxygens and a 2- charge. Carbonate has 3 oxygens. You go up from there. Meanwhile, nitrite only has 1-. So in terms of both number of oxygens and the charge, the second row starts at 2. The number of oxygen goes up from 8 to 8. The number of the charge goes down from 2 to 1. Third row starts at 3, meaning phosphite starts at both 3 oxygens and a 3- charge. And then you go up by 1 oxygen going from 8 to 8, and the charge goes down by 1 going from phosphorus to sulfur. Okay, so that is one way. Just another mnemonic. Might help you, might not. Totally up to you. So, sulfite. Only 3 oxygens, hence it's 8. Sulfur has a 2- charge. Now, this one has a rather complicated thing when it comes to finding the charge, because there's 2 manganese ions and there are 3 sulfites. So, 2 times our manganese plus 3 times our sulfur is going to be equal to 0. The whole thing has to be neutral, and there are 2 of these, there are 3 of these. Okay. So 2 of our manganese plus 3 of our sulfur is equal to 0. Each of our sulfurs has a -2 charge. So 2 manganese minus 6 equals 0. Our manganese has a +3 charge. So a little bit of math. Not the most difficult math, but if you're not that good at algebra, you're going to struggle with this. So again, practice, 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 practice. So this is manganese 3 sulfite. Moving on. Next up, AlCN3. Okay. Well, Al is... Thank you for that, Wesley. Nice of you to snore in the middle of the thing. So, Al is aluminum, or as the British call it, aluminium, because they wanted it to sound like the others. So we look for it on the periodic table. It's over here. It's not on the S block, but it is on the staircase. Silver, zinc, aluminum. Remember the staircase. So aluminum only ever takes a 3+ charge. It will never ever have anything other than a 3+ charge. Therefore, you don't have to tell anyone that, because just naming it as aluminum will be sufficient. So we don't need to indicate what the charge is on aluminum. And then it is paired with one of the more infamous compounds out there, cyanide. Oops, cyanide. The name for this is because it was used in a very, very popular, very bright, brilliant blue dye. So hydrogen cyanide is also known as prussic acid because of the brilliant blue color of the uniforms of the Prussian military. So cyan means that nice bright blue color. So that's one way to remember it. Or you could just say hydrogen cyanide, CN, cyan. That might be a way to help you remember it. In any event, AlCN3 is aluminum cyanide. And finally, we have Ag2O. That is, Ag is silver. So, maybe the name is tickling your memory, maybe it's not, but let's hop over to the periodic table. Here's silver right in the middle. Not in the S block, but again, it's on the staircase. Silver, zinc, aluminum. Silver is always a 1+ charge. So, we don't have to indicate what the charge is on our silver. And it's paired with oxygen. Now, be careful with oxygen. It can be easy to get tripped up. Is this oxide or is this peroxide? If you see an O2, be careful, because it could be either one. In this case, there's only the one oxygen, so it cannot be peroxide. Peroxide will always have the 2 subscript, always have a 2 subscript. Okay, so this cannot be peroxide, this is just oxide. So this last one is silver oxide. The reason you have to be careful of O2 is because you could have something like, well, let's do mercury and oxygen. You could have HgO or Hg2O or HgO2 or Hg2O2. The reason I use these is because mercury and oxygen both have a similar sort of thing with their polyatomic ions, in that you have mercury 1, which is Hg2 2+, and you have peroxide, which is O2 2-. So for both of these, you have to be careful in the exact same sort of way. So here we have just a single atom of each, so no need to be worried about what kind of atom you're looking at. This is just going to be mercury 2 oxide. This one here, okay, this cannot be peroxide, this is just oxide. And we look at what it's bound to, and we see that there are 2 mercury atoms. So this could be mercury 1, or it could be mercury 2, each one of which has a 2+ charge. But because it's paired with oxygen, oxygen has a 2 negative charge. Oxide has a 2 negative charge. So this total thing over here, the Hg2, has to have a 2+ charge total. So that's why we say sort of each mercury kind of has a 1+ charge. It doesn't actually, it's a polyatomic ion, but that's mercury 1. Meanwhile, here we have mercury 2 peroxide. Okay. There's no way this could be oxide. Mercury will only be mercury 1 or mercury 2. There's no particular way. You could know that right now. I'm just telling you for the purposes of this demonstration. So if this were oxide, then that would be a total of -4. This would have to be a +4 to balance it. Mercury can't be mercury 4. So this has to be mercury 2 combined with a peroxide. Meanwhile, down here, when you see an unreduced ratio, then you know you're dealing with a polyatomic ion. Okay. When we write out these compounds, we always write them in reduced ratios. You look over on the left, you'll never see a common divisor over here. There's no number you can divide through. You have a 1-to-1 ratio of ammonium to chloride. You have a 1-to-3. You have 1-to-4, 3-to-1, 1-to-2, 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 2-to-3, 1-to-3, 2-to-1. Okay, you'll never see a 2-to-2 or a 2-to-4 or anything like that. A 3-to-6. Okay, if there's a common divisor, we go through and divide it just to get the simplest possible ratio. There's no common factors. So when you see something like this that looks like it does have a common factor, that is your clue that you're looking at polyatomic ions. Because this cannot be mercury 2 oxide, because that would be a 1-to-1 ratio. So at least one of these has to be a polyatomic ion. And in this case, they both are. Because this right here is mercury 1 peroxide. Okay, Hg2 2 plus and O2 2 minus, one of each. So in a way, the reason it looks like an unreduced ratio, it's not actually an unreduced ratio. Instead, we have our invisible parentheses with the invisible subscripts. Okay, so it's really a 1-to-1 ratio of the polyatomic ions. It is not a 2-to-2 ratio of those atoms. It's a 1-to-1 of the polyatomic ions. And this one here, so here we have a 1-to-1 ratio of mercury 1 to oxide. Here we have a 1-to-1 ratio of mercury 2 to oxide. Here we have a 1-to-1 ratio of mercury 1 to oxide. This third one is a 1-to-1 ratio of mercury 2 and peroxide. And this final one is a 1-to-1 ratio of mercury 1 peroxide. So each one of these is a 1-to-1 ratio, even though we have the number 2 floating around in there. The thing is that 2 is part of a polyatomic ion. Okay, so we have a lot of invisible parentheses and invisible ones floating around in there. Okay. But reducing ratios is important. When we move on to the next bit of practice and do name to formula, you're going to see that. We're going to have to come up with a way to reduce those ratios. Fortunately, that is fairly simple, fairly straightforward. Okay. Going from the name to the formula is a little bit easier in one sense, because they give you the element, then you just have to translate that into the symbol. Unless it's a polyatomic ion. If it's a polyatomic ion, then you're going to have to either just memorize that or, again, go back to the chart. But the other thing is, they tell you straight up what the charge is if it can take multiple charges. So, first up, we have chromium 6 phosphate. So, chromium is Cr, and they're telling us that it has a 6+ charge. Chromium 6. Phosphate. Phosphorus is on the third row. Third row starts at 3. So phosphate is 1 more, PO4. Third row starts at 3 for the charge. Phosphorus is the one further to the left, so it's PO4, 3 minus. Okay. Now here's how you can find the ratio really straightforwardly. Okay, you don't have to be that good at math. Okay. All you do is you bring the charges down. So you have a 3 minus there, that becomes a 3, a 6 plus there becomes a 6, and so you have Cr3 PO4 6. So that is the start of what you're looking at. But like I said, we have to reduce the ratio. 3 to 6 doesn't work. They're both divisible by 3. So you divide both of those numbers by 3. That gives you Cr PO4 2. That is chromium 6 phosphate. So that's why I started with going from formula to name, because this trick works perfectly well going from name to formula. You can bring the charges down to get the ratio, but you can't go in the other direction. If you tried to do that here, you'd be tempted to say that PO4 1 minus and Cr 2 plus, and that is not the way it works. Okay, what the ratio tells you is that the chromium has twice the charge of the phosphate. Okay, it takes 2 phosphates to balance out the charge of the chromium. Okay, and that's because it's 3 minus and 6 plus. So you can't just bring the charges back up. You can't bring the numbers back up in order to find the charges, but you can bring the charges down in order to get the ratio. Okay. So that's why I'm doing this part second. All right, next up we have vanadium 4 carbonate. So vanadium is just V. It has a 4+ charge. Carbonate. Carbon is on the second row. Second row starts at 2. 8 means 1 more. And 2 minus charge. Once again, we bring the charges down. We have 2 and we have 4. Those are both divisible by 2. So 2 becomes 1, 4 becomes 2. You just divide both of them by 2. Thus, we have vanadium vanadium for carbonate is VCO3 2. Now remember, you only need these parentheses if you have more than one of the polyatomic ion. Moving on. 10,2 nitrite. So 10 is one of the ones you had to memorize. 10 is SN, and here it has a 2 plus charge. Then we have nitrite. Nitrogen is on the second row. Second row starts at 2. So ite is 2, but nitrogen is 1 to the right of carbon. We didn't start at nitrogen. We had to move over to nitrogen, so it has a 1 minus charge. So once again, we bring the charges down, 1 and 2. There's no common divisor, so it's just SN NO2 2. And that is 10,2 nitrite. Nope, nothing to add. Okay. Cobalt 3 oxide. Cobalt is CO. 3 means it's 3 plus. Oxide is just O with a 2 minus charge. So we bring the charges down. We have 2 and we have 3. No common factors there, so it's CO2O3. Cool. Titanium 2 acetate. So titanium is Ti. 2 means 2 plus. Acetate, again, there's a couple of different ways to write this. I'm just going to do AC. Acetate, again, until you get this memorized, it's just a 1 minus charge. Not much you can do there. Yeah, bring the charges down, 1 and 2. So this is titanium acetate. Titanium 2 acetate. 1 titanium for every 2 acetates. Or another way to write this is TiC2H3O2 2, or the various other ways there are of writing acetate. Continuing, vanadium 5 sulfide. Oh, I repeated vanadium. How strange of me. Okay, so vanadium 5 sulfide, 2 minus. Once again, we bring our charges down. We have 2, we have 5. No common factor. We can't divide through, so it is vanadium sulfide. Vanadium 5 sulfide. Chromium 3 hydroxide. So chromium, again, Cr. This time it has a 3 plus charge. Hydroxide. Okay, don't let the IDE fool you. This is a polyatomic ion. It's one of the 3 I pointed out. And a way to remember this, hydro means hydrogen, oxide means oxygen. So hydroxide is OH. In terms of the charge, 1 minus, just something you'll have to remember. So this is CrOH 3. Lithium iodide. Okay. Lithium doesn't have a number after it, no Roman numeral, so it is one of the ones where you know that it only forms 1 ion. So is it in the staircase? Oopsie. Is it in the staircase? No, it is not. Silver, zinc, aluminum. So it's over here in the S block, yeah, way up at the top. Li. Okay. It's in the first column. So lithium will always take a 1 plus charge. And this lithium was combined with iodide. Iodide, it's not one of the 3. It's not hydroxide, cyanide, or peroxide, so that means it's a monatomic ion. So we come over here. We're looking at iodine. Iodine becomes iodide. It's a halogen. It's 1 step away, so it becomes 1 minus. So lithium iodide, a 1 plus and a 1 minus. So that means it is just a 1 to 1 ratio. LiI. Ooh. Lead 2 nitride. Okay. Lead is Pb, 2 plus charge. Nitride means we're looking at, again, a monatomic ion. Nitrogen. Nitrogen always takes a 3 minus charge. So this is Pb 3 N2. And finally, silver bromide. Silver and bromine. Silver is on the staircase. Silver is zinc aluminum. It always takes a 1 plus charge. Bromine is a halogen. It's right next to the noble gases. Always takes a 1 minus charge. So silver bromide is just AgBr. If any of you happens to be a photography buff, this is a little bit of history. Silver bromide was one of the first chemicals they used for making photographs. Just by itself, it's a white crystal, but you expose it to light, and it reacts with oxygen in the air, and you get silver oxide, which is dark black in color. So you put it on a piece of paper, you expose it very briefly to light. Places where the light struck it turn black. Places where the light didn't strike it does not turn black. It remains white. And thus you get a black and white photograph. It's an inverse image, and that's why you have your negatives, and then you transfer those onto your permanent photographic paper. We've gotten a little bit more sophisticated since then, but that is more or less how it works. Since then, what we've done is we've added color to it. And we've also digitized it and things like that. All right, so that is name to formula, formula to name. Again, like I said, like I keep saying, like I'll never stop saying, practice, 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 practice. Okay. And you absolutely have to be careful of your peroxides, and we have to be careful of peroxides as well. Because look at this guy. This could be either of two different compounds, okay, depending on whether this is oxide or peroxide. If it's oxide, then you have two oxide ions. If it's peroxide, then you have one peroxide ion. So in order to balance this, your single oxygen atom would have to have a 4 plus charge. In order to balance this, it would have to have a 2 plus charge. So just with this formula, you could have two very different ions. You could have lead 4 oxide or lead 2 peroxide. So that's why we don't just rely on formulas, why we also have to have names. Well, that's one of the reasons. That's just, again, a note. Be very careful about mercury 1 and peroxide. Those guys can fool you. They can screw you up. And practice, 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 practice. And that is it for this particular set of slides. And this took a lot longer than I thought, but the next sets of slides should be easier. Yes, they will. So I'm going to go ahead and finish those up tonight. I will see you in, call it 5 minutes, for